How can we make a tennis ball bounce up without touching it? How can it be done? This is a magic trick. The ball is bouncing up. Let's take a look at it again in slow motion. Actually, there is a vibrating tuning fork which makes the ball bounce outwards. How can a tuning fork vibrate by itself? Let's zoom out. Now you see that there's actually another tuning fork next to the first one. The two tuning forks are exactly the same, and they have the same vibration frequency. If we place both tuning forks on a table and hit one of them, the other one will also vibrate. This is a physical phenomenon known as resonance. Each object vibrates at a particular frequency according to its own physical properties, size, shape, mass, etc. For example, if we knock on this window, it always vibrates at a particular frequency. We call this frequency as natural frequency. There are 3 tuning forks on the table. 2 of them have the same vibration frequency, while the third has a different frequency. Guess what will happen if we hit just one of them? Due to the resonance, the 2 tuning forks with the same frequency vibrate together and generate sound, but it seems nothing has happened to the third tuning fork. As the natural frequency of the third tuning fork is different from that of the one which starts the vibration of the third fork is so small that it's hardly noticeable. It may be easier to understand resonance if we look at the movement of a swing. A swing will swing back and forth with its own natural frequency. If we want the swing to go high and fast, we need to push it at the right time in accordance with its natural frequency. Only then will the swing move with great amplitude at resonance. How about resonance in sound? Listen carefully. What is that sound? Even the air column in a wine glass has its own natural frequency of vibration. Rubbing the rim of the glass gently can make the glass vibrate. When the frequency of vibration of the glass matches that of the air column will resonate and produce sound. This is similar to the movement of the swing. Electromagnetic waves and electrical components can also be set into resonance. The tuning of radio and TV channels is actually achieved by altering the resonance frequency of the resonate circuits to match that of the radio waves. The electric current of the circuit will be the maximum at resonance. Once the circuit is tuned to receive the specific radio waves, we can receive the strongest audio and visual signal of the designated program. David! Laser beam is a strong and powerful beam of light. Its intensity is high because it's a coherent beam of light. It is produced by optical resonance and an optical cavity called laser.
Raymond, music.
David, which kind of music you prefer?
Violin and piano.
Any favorite song?
You choose.
Okay, we'll play Climb Every Mountain.
2 identical musical notes are played on a violin and a piano. Although they are of the same note or pitch, you can easily distinguish between the unique sounds produced by each. The same musical notes produced by different musical instruments sound different to the ear. This is because of the difference in timbre. What does that mean? The answer may be found if we compare the waveforms of the notes generated by different musical instruments. This is the waveform of the sound generated by a tuning fork, and the other one is by a violin. Let's look at the shapes of these waveforms. Although the shape of the waveform generated by the tuning fork is a simple sinusoidal curve, whereas that by a violin is more complicated, the distances between two consecutive waves in both cases are the same. It means that the two musical notes have the same pitch. Why do the sounds sound differently to the ear even though they have the same pitch? The answer is in the shape of the waveform. The shape of the waveform determines its timbre. Sounds generated by violins and pianos have different timbres because the shapes of the waveforms of the sounds they generate are different. Why is the waveform of a violin more complicated while that of a tuning fork simpler? This is because the waveform of a violin is composed of a fundamental frequency superimposed with one or more waves of multiple higher frequencies. This complicated waveform is what determines the unique timbre of violin. At this point, we need to introduce the concept of the superposition of waves. When two waves from different sources meet, the resultant displacements of wave is simply the algebraic sum of the displacements of two individual waves. This is called the principle of superposition of waves. When a wave with a simple sinusoidal waveform, such as that produced by a tuning fork, overlaps with a wave 3 times its frequency, a more complex wave will be formed. The wave generated by violin can be viewed as the resultant wave of the superposition of several waves of a simple waveforms. Once again, sounds are generated by the vibrations of an object. When the body of an object vibrates, it will generate a fundamental tone. The other parts of the object will also vibrate. These vibrations add up to generate overtones. It is the combination of overtones that determines the timbre of a sound. Sounds can be distinguished by their timbres even if they may have the same tone and loudness. Listen to this note once more. Is this the sound of a violin or a piano? Does light exhibit the same phenomenon? We can find the answer if we shine a beam of light through a prism. When the light beam passes through the prism, a color spectrum is formed. What does that show? It shows that white light is composed of a superposition of various colors. The prism merely splits the white light into various colors. Isn't it strange that the superposition of all these colors results in white light, and yet white light is not really white in color? This requires a bit of imagination. There's a happy duckling on a calm pond. It kicks rhythmically in the water, setting ripples that disperse outwards. As the ripples disperse outwards in the same medium, they carry the same speed. It then creates a set of concentric circular waves at equidistant from each other. If the duckling kicks twice in 1 second, then the two waves will be observed in 1 second anywhere around the pond. This is also the frequency of that water wave, that is 2 Hz. What would happen if the duckling kicks and it moves to the right? The waveforms in front of the duckling will be closer apart, while that behind it wider apart. At the front side of the duckling, more than 2 ripples will be observed in 1 second. It means that the frequency is higher than 2 Hz. However, at the rear side of the duckling, fewer than 2 ripples will be observed in 1 second. It means that frequency is lower than 2 Hz. The result of the duckling kicking while moving forward is that an observer in front of the duckling will observe ripples with a frequency higher than 2 Hz, while an observer behind the duckling will observe ripples with a frequency lower than 2 Hz. That's amazing! This phenomenon applies to all types of waves and is known as the Doppler effect. The Doppler effect is the change in frequency of a wave when there is a relative motion between the source and the observer. the effect doesn't actually change the frequency of the source. In the case of the duckling, when the duckling moves forward, it is still kicking twice per second. To an observer in front of the duckling, as the distance from the duckling decreases, the distance between two successive waves, that is, the wavelength decreases too, and so it feels like that frequency has increased. To an observer behind the duckling, as the distance from the duckling increases, the distance between the waves increases too, and it feels like the frequency has decreased. David, are you sure you have to go to space? What will be the case in sound waves? When an ambulance is moving forward while its sirens are on, passers-by at different locations will hear the siren sound differently. The ambulance is at the center of the circular wave that it generates. As the source of the sound waves moves forward, more densely packed waves, that is, waves of higher frequency, will be received in front of the source. Conversely, more sparsely packed wave, that is, waves of a lower frequency, will be received at the rear of the source. Therefore, when an ambulance with the sirens on moves closer to and then drives past an observer, the sound heard will change from a higher-pitched sound to a lower-pitched sound. Likewise, in astronomy, the frequency or wavelength of light emitted by moving celestial bodies also changes. The Doppler effect is what causes the seemingly changed colors of the lights. When a star is moving towards or away from the Earth, its color will change because of the Doppler effect. Let's investigate this carefully. When a star is moving towards the Earth, the light is emitted as observed from the Earth will seem to have shorter wavelengths. The absorption lines in the spectrum shift to the blue side, that is, to shorter wavelengths. This is called blue shift. On the contrary, when a star is moving away from the Earth, the wavelengths of the starlight increase and the absorption lines shift to the red side, that is, to longer wavelength. That is called red shift. The Doppler effect has a wide range of applications in astronomy. By observing the changes in the wavelengths in the spectrum and applying the Doppler effect, the orbital motion of stars can be analyzed. There is another situation that is related to the duckling. What happens when the duckling moves faster and faster? When the duckling moves forward and reaches a certain speed, the ripples generated will no longer be circular, but rather in a V shape. Why is that? When the duckling moves at a speed higher than that of the water wave can't catch up with the duckling. So a V-shaped wave pattern instead of a circular wavefront is formed. Sound travels in the air at a speed of approximately 340 meters per second. It is really fast, but humans have already achieved supersonic flight. When a jet flies at supersonic speed, the sound boom, boom can be heard on the ground. This sound is known as sonic boom. Why does this happen? Let's find out the answer. The situation is actually similar to the duckling on the pond. When a jet is flying at supersonic speed, the sound source is moving faster than the sound wave it generates. There is no sound waves in front of the jet because the sound waves can't catch up with the speed of the jet. When the waves reach a concentrated point at the same time, a shock wave is formed. A jet flying at supersonic speed will generate two shock waves. The first shock wave is formed when the compressions of the waves generated at various time instants superimpose to give a conical wave front. The second one at the rear of the jet is formed when the refractions of the waves generated at various time instants superimpose. These two shock waves spread out behind the jet and eventually reach the ground where it causes the sonic boom. David! It seems that nothing can travel faster than light. Is it possible for shock waves to happen in light? Not really. When light propagates in a medium such as water, its speed is slower than when in a vacuum. In certain environments, such as a nuclear reactor or a particle accelerator, charged particles can be accelerated to a speed higher than that of light. This will lead to the generation of electromagnetic radiation similar to a shock wave of light. David. Then a characteristic blue glow will be emitted. It is named Cherenkov radiation, after the scientist Cherenkov, who was the first to detect it experimentally.